Sorry for those who are at home. We lost about 20 minutes in the recording. But the way I wanted to end here is this has to be tilted that way, like that, and this has to be like that. So these two are perpendicular to each other. So when you have multiple bonds, when you have double bond on one side and double bond on the other side, the pi bonds are perpendicular to each other.
Do you have the models? Do you have like the physical models?
These things?
Yeah.
These don't do a good job.
No, never mind.
I'll show you why. You're going on with biology and chemistry and stuff, right?
Both of them, yeah.
I'll show you why these suck.
Great.
Why I tend not to use them. These don't show the two lobes. They fool your brain. That's a double bond. Uh-oh. This gives my brain a chance to relax. This is that's a double bond. But it looks like the two lobes of one pi bond. So it doesn't show that. It doesn't show this stuff.
So it should be tilted, like perpendicular.
No. It will show it tilted. My problem with these is they don't show a sigma bond and a pi bond. They show both. Another problem with these, and they aren't all color-coded the same. The second black one here, pretend the black one on the end is yellow. All right, this does force these to be not planar like they should. My problem with this is one sigma bond and one pi bond. So you have to look at that as a sigma bond and that as a pi bond. What I wish they had is something that went straight in between for the sigma, and then those two represented one pi bond.
Okay.
But that's just, you see what I mean?
Yeah.
That's why I don't like these. This day and age, I would think somebody could engineer these to do that a little better. So I lean away from these because of that. I would say the best thing to do is learn, these are free on the web too, something called MolView. You can build molecules in it, MolView. You can build molecules in it and click a button and it creates a three-dimensional model over on the right. You can rotate it around and look at it.
That would be so much easier because I'm like a very visual.
Yeah, me too. All right. Nice little design. GeH4. Don't want to center that. HCN, yes, let's do HCN. Triple bond. I also want to do, all right, we'll do HCN, probably SO2. All right, HCN. If I gave you HCN, there's a pair there. All right. So that's the Lewis structure for HCN. Carbon. How many electron domains around carbon? Come on.
2.
And what's the hybridization? This is too easy to miss on a test. SP. So it would go SP, SP, 2P. You've got a sigma bond here and one sigma bond here, so you've got to have that. And then you've got a pi bond and another pi bond, both going to nitrogen. Okay, that's carbon. And I erased all that. Yeah. So that's nitrogen. How many electron domains around nitrogen?
2.
2 again, so its hybridization is
SP.
SP. And now we have 1, 2, 3. Look at nitrogen, you've got one lone pair, and you have one pair going in a sigma bond. And, one electron going into a sigma bond, one electron going into a pi bond, and another electron in a pi bond. So you've got 2 pi bonds that need to pair, so 1 electron each. And then you've got one sigma bond that needs to pair, so that's 1. So that tells you that your 5 electrons go into this way. 1 electron for one of the pi bonds, 1 electron for another pi bond, and 1 electron for a sigma bond, and then a pair by itself. So that's going to be how nitrogen is when it's hybridized. I know that question is probably just asking for central atom here would be carbon, so the answer to that question is actually SP. But let me draw it out so we can interpret the diagram. Carbon, SP, SP, but nitrogen over here, SP, SP, and here's your pair. And it's got leftover pi bond there, and a leftover pi bond coming straight out at you. And both of those have 1 electron in them. Carbon has this and this and this and this. Carbon has 1 electron in each one of these. Do it up here, down here. So these 2 electrons pair and they do this. That's the one that's going out like this. And these are the ones that are in the plane of the board. I kind of used his notation there. Dr. Herbert, the guys that teach 1211 and 1212 are, if you were thinking about going to graduate school, they're really good teachers for that. That's another way of saying they're hard asses. It's a harder class than mine because they assign tons of homework and managed to get to everything that I didn't. That's good or bad, depending on the way you think. And of course, that hydrogen is out here, it's just in a 1s orbit. So these are perpendicular to each other. All right. SO3. What else do we have? I guess we could do that, so. C2H6, so I did C2H4 and C2H2. Let's see what happens with N2H4.
Isn't it just a single bond over?
I'll draw it like this. Now let's keep it like this. Single bond, pair. Okay, that's right. What's the hybridization around? The ends are the same, so what's the hybridization around nitrogen?
ST3.
sp3. 4 things around it, so it's sp3. So nitrogen, both nitrogens will look like that. You got to get 5 valence electrons in there. One of them is a pair, and the other ones are single electrons. So the nitrogens look like that. I'll draw the other nitrogen, just so I can sort of diagram this. One of them, the 2 nitrogens are pairing with each other, and one of those go to hydrogen. This will go to the other hydrogen. That'll go to hydrogen. Not that hydrogen. So just to sort of sketch it out. N. I won't try to draw the tetrahedral shape. But there's no pi bonds here, and you can tell that immediately by looking at this. There's no double or triple bonds, so there's no pi bonds. All of these do direct overlap with each other. Nitrogen, hydrogen, hydrogen. I drew the hydrogens up, so I'll do this one that way. But it's equivalent to do it either way. And then down here, these are those pairs of electrons. sp3 orbitals, these are just s orbitals, the 1s. I really don't think there's anything else. I'm curious what they asked, but let me hit a couple high points, a couple of other things I want to mention. Just because they're straightforward enough, I can do them quick. This would have been earlier in the semester, so we can get away from this stuff a little bit. But it's just too obvious. I know it's going to be on the ACS test, so I don't want to skip them. One of the things I did go over, was it you that mentioned isomers? I mentioned it briefly one day, and I think I dropped it because there's no good questions in here about it. At the end of there's questions at the end of the chapter, but it's a very straightforward concept. So, let me just double bond there. Nitrogen. And we don't need the pairs, but if I wanted to put in the electron pairs, that's where they'd be. All right, if you're given this structure, you could probably, if you picked A, B, C, or D, you could probably pick C3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Did I count that right? That's right, that's right, that's right, that's right. Okay, so if you had this structure as a Lewis structure, you can see why that would be the chemical formula for it. Because I'm just adding things up and logging them in up here, sort of tallying them up. The idea of an isomer, I have 3 carbons, oxygen, 2, 5. Gotta make sure I did that right. 2 bonds, 4 bonds, 4 bonds, 3 bonds. And if you wanted the pairs, that would be 2 on oxygen and 1 on nitrogen. 2, 3, 4, 5. Yeah, that's good. If I ask you to give me the chemical formula of this, or to take A, B, C, or D, you have C3. You'd have the same chemical formula, that's the point. These are isomers. They have the same chemical formula, but different structures. It's that simple. That's what isomers are. You can bend over backwards to try to make it a complicated problem to solve, but the ACS test doesn't tend to do that. One thing to notice here, if I had a third one here, that would be the H upwards. That's a double bond. Missing a double bond. That's double.
Is that a carbon to carbon next to the nitrogen?
That one. And let's
And
do
that
that
bottom
one.
hydrogen needs to.
Carbon to carbon. Let's do that one up. And then in with the hydrogen double bond C. That H should not be there. Do that H up. There's those. All right, and let me get kind of stupid. H. Down, carbon. One more hydrogen here. H, nitrogen, carbon, double bond carbon, hydrogen and a carbon, 2 carbons, oxygen, hydrogen. So this, and this are not isomers. They're the identical molecule. And if there's any games to be played with this simple concept, they'll do this bullshit to confuse you. They'll have this, this, and this. And you're just going to have to use your, because the Lewis structures only show you what's connected to what. There's no 3-dimensional information in them. What's connected to what is the same here as it is here as it is here. All of those you could describe this way. You start with a hydrogen, single bond to an oxygen, single bond to a carbon. That carbon has 2 hydrogens, but it continues with a single bond to another carbon. That carbon has a single hydrogen, and then it has a double bond, where am I? To a nitrogen, and that nitrogen has 1 other hydrogen on it. You could describe all of those 3 of those that way. Just if you described it in a paragraph describing what's connected to what. This is a picture of what's connected to what. These are too, but they are identical. So if they try to make a simple concept difficult, they'll do that. So let's say you had all 4 of these, and you had to say, which ones of these are identical and which one of these are isomers? A, B, C, and D are identical, and A, B, and C, and D are an isomer of B. That's the only way to make this complicated. But it's as simple as this if you're being nice about it. They all have this chemical formula. So you can have the same chemical formula and be the identical molecule, obviously, but you can also be a different structure altogether. These are connected up differently. These are all connected up the same, despite the asshole-ish way to draw them.
Is there going to be like cis trans and enantiomers on there?
This book didn't hit cis and trans, so you usually run into that once you take organic chemistry.
Okay.
Cis, trans. Yeah, I don't think it's on the ACS test, believe it or not. I don't even think they do it in 1212. You have to take organic to see it. It's a simple concept
But
too.
why did I learn it?
I don't know. You really have to pick and choose what you're going to do when it comes to. All textbooks are a little bit different in what they omit and what they include. They're also different in the way to describe things, and they also use sometimes slightly different nomenclature. So I wish it could all be neatened up the way I think. There's that, and then some other simple things. Right at the beginning of the semester, I jumped right over some things that I think are just so obvious later. I think you probably know solid, liquid, gas. Things are solid at some low temperature, and then they get higher temperatures, they eventually turn liquid, and then higher temperatures they'll turn to a gas. That's true of all molecules. It's true of ionic compounds and molecular compounds as well. It's just ionic and molecular compounds have to be at very, very, very high temperatures just to melt from solid to liquid. All across the universe and on Earth, you have to be to thousands of degrees, regardless of which scale you use, Kelvin, Fahrenheit, or Celsius. It's thousands of degrees to get those to melt in the first place, much less get them to turn into a gas. So you focus on molecules here if you want to say anything. In all molecules, that's the order it goes. Colder temperatures, they're solid. Kind of a medium temperature, they're liquid. Higher temperature, they're gas. Some things are solid at room temperature, so anything around here that's solid is solid at room temperature. A lot of things we could melt here to not thousands of degrees, but hundreds of degrees. They'd melt, the plastic would melt, because that's molecules. Anything molecular is going to melt a bit higher than that. And most of them, you get them to turn into a gas at reasonably low temperatures compared to thousands of degrees. So you probably know that. If they're depicted in a diagram like this, the ACS test will do this in black and white. But if they're far apart from each other comparatively, and this is true when things are a gas, aka a vapor, the molecules are far away from each other. When they're liquid, they're closer, but they're not connected to each other. They're still able to sort of swim around each other, but they're all together in a container. And when something is frozen, everything stops. Oh, that's neat. Oh, what happened?
The Zoom.
Whatever. I think that picture's better. But things start lining up in sort of a lattice shape when things are a solid. Ice is the solid here. We have these special words for water, vapor and ice. Okay, pure substances. In this diagram, it's showing separate atoms. Things completely separate like this, it's probably only the noble gases. But if you had any set of atoms that are all apart from each other, you can call that elemental. And if you have molecules like H2, H2, N2, O2, F2, Cl2, and Br2, and I2. Those are still, we call elemental, but they're just in the form of molecules. So this diagram is helpful. Atoms of an element, molecules of an element. Once you have more than one thing together as a molecular substance, then you call it a compound. That's the word we use for it's a compound. I don't use that word much. I usually just say molecule. But those are called compounds. And then this, now they step into the idea of a mixture. So you see an elemental compound here, elemental here, and a compound here. Molecule is an element, compound. But when there's more than one thing all mixed together, it's called a mixture. That's pretty obvious, right, that word. And then, no, they won't ask that. They won't ask that. I'm just trying to get to heterogeneous. This works if you're trying to decide something, but I think this flow chart is more than you really need to think. You could memorize it if you wanted to. Well, there's one more diagram I want. Maybe I missed it. Give me a second. We'll end a little early. Let me just find one more. I don't think they do these space filling models on ACS exam. The idea of a heterogeneous mixture and a homogeneous mixture. Solid liquid gas. I guess this is where I saw it. They have a diagram like this on that in that practice material that we'll do when y'all come back. No. Okay, don't worry about it. It's a simple thing, but maybe I'll find it. So let's take a break, come back at 2, and decide if you're doing makeup labs, which labs you need to make up. And I'll have this out when you get back. If you know right now, that's fine. You can do it now, but I'll put them over here. Do sign in if you did. But write down what lab you need to do. This is just a schedule of the labs we do. Remember, there's something out there we switch off. All right. When you come back, write down the date that you missed and the lab you missed. I forgot which one of these you changed, but there's something else. I'll look at my notes and figure it out. I'll see y'all back here at 2.
Dr. Emery,
Yeah.
did you see that email?